In this video, we will be discussing about the overall heat transfer coefficient. Here you can see a heat exchanger, which you can name it as a tubular or double pipe heat exchanger based on constructional feature, and based on the flow arrangement it is coming under a parallel flow heat exchanger where both the fluids are entering and flowing in the same direction. Here the inner fluid, which is flowing in red color, we will be naming it as the hot fluid, and this green fluid will be known as cold fluid. So whenever it is flowing through this two tubes, heat will be exchanged from hot to cold fluid through the walls of this brown tube. So heat exchange will be transferring across this direction, and if you are seeing the cross section, this is representing the brown tube, inner tube, through which red fluid is flowing, and around it which the cold green fluid is flowing, and heat will be transferred across the section. If you are looking for some part of this tube, then inside hot fluid will be there and outside cold fluid will be there. The heat transfer occurring is named as Q. So if you are looking for the phenomena by which heat transfer or heat exchange is happening from the inner fluid to the tube surface, the heat will be transferred by convection phenomena. Here convection phenomena will be occurring, and along this tube surface through the metal, conduction phenomena will be occurring, and at the outer surface, from this outer tube surface to the outer cold fluid, again convection phenomena will be occurring. So these are the three ways by which the heat is being transferred from the inner hot fluid to cold fluid. If you are looking for the heat flow, there will be different resistance will be associated with this: convection resistance, conduction resistance, and again convection resistance. So if you are looking, HI will be named as the heat transfer coefficient for the inner fluid and this inner surface, and HO will be the heat transfer coefficient for outer fluid and outer surface of the tube. K will be named as the thermal conductivity. Ri and Ro are the inner and outer radius. So from the electrical analogy, you are having the heat flowing will be equal to the change in temperature from innermost and outermost divided by total thermal resistance. If you are looking for the thermal resistance here at the innermost, that is here, if the temperature is Ti, then this point will be representing Ti, and again some resistance will be coming. First resistance will be for convection, inner convection resistance, and again second resistance will be for conduction resistance through the tube, and last resistance will be for the convection at the outer surface, and then it will be reaching the final temperature. So this delta T is Ti minus T naught. So first inner convection resistance will be 1 by HA is the convection resistance. Generally here it will be naming as HA into AI, where A is the inner area, inner surface area, and this next resistance will be conduction. For a cylinder it is 1 by 2 pi L K, where K is the thermal conductivity, into log R outer divided by Ri. This we have studied in the first module or convection chapter. Then the last resistance will be again 1 by HO into area outer, where inner area you can find it as inner area is 2 pi into Ri, inner radius into length of the heat exchanger, and outer radius is 2 pi into Ro into L. This is the total resistance. Mean I can write it as Q equal to delta T the whole divided by 1 by Hi into Ai plus 1 by 2 pi Lk into log Ro divided by Ri plus 1 by HO into AO. These three resistance are coming because convection, conduction, and convection phenomena is occurring while heat exchange. Here we will be discussing about the overall heat transfer coefficient. Means if you are able to represent the heat flow or heat exchange between this hot and cold fluid by, that means this Q, if you are able to represent by convection only, means if you are able to represent by convection phenomena only, so then convection will be having, this can be represented form of convection by Newton's law of Cooling is H into A delta T. Means this will be, this you can represent in that form, you will be calling it as H into A into delta T form we can represent. So if you are representing this Q phenomena by convection only, here convection, conduction, and convection is happening, but we will be replacing it by convection phenomena only. Then you can represent this Q as some, instead of H we will be naming it as U, which is known as overall heat transfer coefficient. U into A into delta T. This delta T and this delta T are same. So here this U will be known as overall heat transfer coefficient. See here, two areas are there, inner area AI and outer area AO. So you can define this overall heat transfer coefficient with respect to both areas. If you are using inner area, then this will be known as UI, overall heat transfer coefficient with respect to inner area, UI AI into delta T. Or if you are using the outer area, then you can write it as UO AO into delta T, where UI is known as overall heat transfer coefficient with respect to outer. The expression for both you can find if you are equating this one. So we can find the expression for this overall heat transfer coefficient based on inner as well as outer area, for which we will be equating. So this one I will be writing here. This is actually representing the heat transfer, actual heat transfer with this convection, conduction and the outer convection resistance. And we will be replacing this entire heat transfer by a convection phenomena only, which you can write in terms of, instead of H I will be writing U, which is known as our overall heat transfer coefficient. It can be defined based on UIAI delta T or UAAO delta T. Then if you are rewriting or if you are finding the expression, then first I will be equating to UIAI delta T, then UI will be equal to 1 by A into this term. If you are simplifying, AI is actually 2 pi Ri into L, then this will be simplifying. This will be equal to 1 by Hi plus Ri by K into log Ro by Ri plus Ri by Ro into 1 by Ho. Here AO will be equal to 2 pi Ro into L. So this will be getting to this form. And this is known as overall heat transfer coefficient based on the inner area. That's why we are calling it as UI, which unit will be equal to watts per meter square Kelvin, same as that of H, because it is representing the heat transfer coefficient. Similarly, you can find the expression for heat transfer coefficient based on the outer area also, where UO will be calling. You can find based on the same expression by equating the actual delta T by total R thermal equal to UO AO delta T. Then you will be getting this expression. This is the overall heat transfer coefficient based on the outer area. Next we will be talking about the fouling and its effect on the overall heat transfer coefficient. So far we have discussed a pipe whose surface are relatively new, but when the tube or this pipe is in use, the surface of this pipe will be getting fouled, means scalings or deposits will be formed. This may be due to impurities or chemical reactions or rust formation. So as a result, the scalings formed around the pipe surface are shown. This is the fouling effect on the inner surface, and this is the showing the fouling effect on the outer surface. So this will be affecting the heat exchange between the hot and cold fluid around the surfaces. So the effect of this fouling phenomena on this heat transfer coefficient we will be seeing. So in the last case we have discussed, the different resistance coming are convective resistance at inner, conductive resistance for tube and convective at the outer surface. But along with this, the deposits will be providing additional resistance, which we will be calling as fouling resistance. So with respect to the deposit at inner side, fouling resistance will be coming at inner, and also fouling resistance will be coming at the outer. So I will be representing here total 5 resistance will be coming. Additional are fouling resistance inner and fouling resistance outer. This is inner convective, fouling resistance inner, conductive resistance of tube, fouling resistance out, and convective resistance out. So if you are finding the total heat transfer, Q equal to delta T by total R thermal. Here these two terms will be coming, and this you can represent for the convection phenomena only, where you will be finding the new heat transfer coefficient. This is known as overall heat transfer coefficient, and here I am mentioning it by star, means you are finding the effect of this fouling, or this is actually the overall heat transfer coefficient of dirty pipe you are evaluating. Dirty pipe means is fouled pipe. This ui star will be based on this dirty pipe based on inner, and u star o will be representing the overall heat transfer coefficient based on the outer. This will be based on the outer. So if you are equating these two equations, then you can find the expression for u star I inner and u star outer. First you will be finding the overall heat transfer coefficient of the dirty pipe. This is star, means dirty pipe. You will be equating, so total resistance will be coming, and here you can this a delta t will be cancelling, then 1 will be coming in numerator, ai will be coming in the denominator. So ai into ai 1 by hi you will be getting, and along with this fouling resistance you will be multiplying ai. So this fouling resistance into ai we will be calling a factor which is known as this fouling factor, and I will be writing the product of fouling resistance and area as fouling factor. This is fouling resistance at inner into area inner will be giving fouling factor at inner RFI. Similarly, this will be getting ai is 2 pi ri into l. This 2 pi l will be getting cancelled, ri by k into log ro by ri, plus fouling resistance at out on here you are having. This will be multiplied. Here I will be multiplying by an a naught in numerator and a naught in denominator. Then this ai will be coming here. So fouling resistance at outer into a outer, I will be calling this product as fouling factor at outer RFO. Then you are having ai by a naught. This you can write it as ri by ro, and plus this term is coming, ai divided by ao will be giving ri by ro into 1 by ho. So if you are simplifying, you will be getting the final expression for the overall heat transfer coefficient for the dirty pipe where you are considering the effect of fouling. So this RFI is actually, this is known as fouling factor, whose unit will be, the unit of fouling factor will be meter square kelvins per watt, and fouling factor you are getting fouling resistance into area. If you are multiplying fouling resistance at inner into area at inner, you will be getting RFI. The unit of fouling resistance, this is just a thermal resistance, its unit will be kelvins per watt, and this is area unit is meter. So you will be getting fouling factor units will be meter square kelvin per watt, and this expression will be getting before after simplification. So this will be giving overall heat transfer coefficient of the dirty pipe or the where you are considering the fouling effect, and this is based on inner area. Similarly, you can equate that q2 u outer star into a outer into delta t. On simplification you will be getting this one, where RFI is the fouling factor. This is not resistance. Resistance into area will be giving you the fouling factor RFI, and this will be RFO, and this UO star will be giving you the overall heat transfer coefficient of this dirty pipe based on the outer area. And here consider in the last case overall heat transfer coefficient, if you are considering your pipe is fresh, then you are having this much resistance only, then you are having this delta T by total thermal resistance equal to UI into AI. So from this delta T will be cancelling. If you are finding 1 divided by UIAI, 1 divided by UIAI will be giving you this expression, 1 by HAI plus this expression you will be getting. And from here you are having UI star AI into delta T equal to delta T divided by this total thermal resistance. From this equation also I will be finding 1 by UI star into AI. If you are finding 1 by ui star into ai, you will be getting this expression plus the fouling resistance. Here fouling resistance fouling resistance at inner and fouling resistance at outer are coming. So this terms will be coming here, and I will be writing the sum of this fouling resistance inner and outer as total fouling resistance. If you are comparing this to equation, you will be getting fouling resistance will be equal to 1 by ui star ai minus 1 by ui into ai. If this is expressed in terms of inner area or inner overall heat transfer coefficient, this can also be written as 1 by UO star AO minus 1 by UOAO. This is the fouling resistance you can find. Remember, the unit of fouling resistance is meter square kelvins per watt, and fouling unit of fouling factor is meter square Kelvin per watt, and fouling resistance is Kelvin per watt. So in this video we have learned about the overall heat transfer coefficient and the effect of fouling factor on the overall heat transfer coefficient. And why we have studied the overall heat transfer coefficient? For a heat exchanger, the exchange of heat will be occurring around the surface. So here you can use this overall heat transfer coefficient for finding the amount of heat that is exchanged between. That will be analyzing in detail, and in next video we will be studying the logarithmic mean temperature difference method, which is used for finding the heat exchanged in this heat exchanger. Okay, thank you.